Hi there, welcome to lecture 10 of Machine Learning from Data. We're going to be talking about nonlinear transforms, which are a very simple but powerful add-on to linear models. Okay. Now first, let's recap where we were from last time. Okay, so we've talked about the linear model, and specifically the linear signal, which is W transpose X. The linearity in W is what we really cared about when we meant linear, and that's what makes the algorithms go. The linearity in X is also important. That's what gives us the linear separator. Okay, and today we're gonna discuss how we can sort of keep the linearity in W so that all our algorithms will continue to go, and somehow relax the need for linearity in X and I'll allow more complicated separators. Okay, but that's a little preview of what's to come. With respect to the linear model, we showed that we can address different kinds of problems by taking this linear signal and transforming it. You apply the sign to get classification. You don't do anything to it if you're doing regression. And if you're doing a probability prediction or logistic regression, you apply that convenient sigmoid that we talked about last time. Okay, and each of these problems, approve or deny credit, that's classification, comes with a learning model, the perceptron, and an error that you try to minimize on the data, the classification error, and algorithms for picking the hypothesis, the PLA or the pocket or regression for classification and so on. If instead you're trying to predict the amount of credit, then we're talking about regression, and we're minimizing the squared error, and we describe the pseudo-inverse single-step algorithm that gets you to the best hypothesis. Okay, if instead you want to predict a probability, so we're talking about logistic regression. Okay, and here the appropriate error which has a probability interpretation is the cross entropy error. So you grade the hypotheses in your hypothesis at the linear model using the cross entropy error, and we discuss gradient descent or stochastic gradient descent as an efficient method for picking a hypothesis from the hypothesis set, i.e. the linear model with the sigmoid applied to it. So picking one of those hypotheses that minimizes the cross entropy error. We can minimize the cross entropy error pretty efficiently because the error function that we derive, this cross entropy error, is very well behaved. It's not only having this probabilistic interpretation, but it is convex, so it has a single global minimum. Okay, now today we're going to continue talking about the in-sample error, and I will remind you, okay, in figure A is one, there are different ways in which non-separable data might present. Okay, now in A, I'm showing you the situation where you have basically linearly separable data, but a few outliers. So there's red X and there's blue circle. Okay, so you'd like to keep the linear model, but tolerate outliers. Okay? And that's what we discussed when we talked about the perceptron with the pocket algorithm, so tolerating outliers or regression for classification. Okay, so today we're going to be illustrating mostly with respect to classification, but everything we say today can be applied to regression and logistic regression. Now, on the right, I'm showing you a different kind of non-separability. Okay, on the right, it's not the case that you can find a linear separator that more or less works with a few errors. Okay, no matter where you put your linear separator on the right, you're going to make a lot of errors. So, for example, think of something like a diagonal linear separator. It's going to get approximately half the blue wrong and approximately half the red wrong, as opposed to a few outlier mistakes. Okay, so on the right, we need something fundamentally different from just an algorithm that can tolerate errors. Okay? And if you think about it, when you look at these blue circles, you see, they somewhat form like a region in the middle. So rather than separating blue from red with a line, maybe we can separate with something like a circle or an ellipse. And that's a totally different model than the linear model. Okay? What I'm going to show you today is that we can essentially keep all the technology of the linear model and solve the problem on the right and get circles. Okay? And the technique that we're going to introduce is the technique of the nonlinear feature transform. So essentially, we're going to transform the X space. We're going to transform the features so that the linear model can still solve the problem. So we can still use all our old favorite algorithms, PLA or pocket, regression for classification, regression for regression, or gradient descent to minimize the cross entropy error. Okay, and so that's the topic of today, nonlinear transform. And let's go to the board. Okay, so let me show you the basic idea of the nonlinear transform through an example. And let's go back to our credit approval application. Okay, and I'm going to put income here. Okay, I, and years in residence Y. Let me put that on this axis. And let's think about credit approval. So for a particular number of years in residence, you might need a certain income above which you will be approved. As I increase your years in residence, that threshold is going to drop. Okay. But now, if you think about it, and this is a phenomenon that happens very often in the real world, it's what's called saturation. As you have more and more years in residence, I don't care. I don't care about the difference between 25 years and 26 and 30 and 40. Once you've been in residence for a long time, you're stable. Okay. So this threshold above which you're going to get credit is going to flatten out. Okay. And the same thing on the other end. I don't care about the difference between 6 months and 5 months and 3 months and 2 months. Once you have not been in residence for a long time, you're unstable. So this threshold is also going to saturate and flatten out. Okay? And so, the classification boundary looks like that, and this is going to be your plus region, and this is going to be your minus region. Okay? So, and when we think about this problem, we see that the linear model is not right, except it's not really that the linear model is not right, it's just that our feature y that we are capturing is not the right feature. So we should, when we sit down and think about the problem, we should realize that the real world has saturation phenomena. And so when we collect this feature y, we should incorporate the saturation phenomenon in the feature y. Okay? What that means is I'm going to take my feature y, years in residence, and transform it to, let's say, a new feature z. And how does this transform look? Okay? What it should do is it should take, y, okay, and when the values of y are very, very large, they should all map to the same value of z. So it should look something like this, and then it can become linear. But again, when y gets very, very small, now we don't care, and so it should saturate on the other side as well. Okay, so this is an example of a transform of a feature that incorporates saturation of the feature. It says once the feature gets above a certain value, it's just high, and once it gets below a certain value, it's just low. Okay? What will that do to this decision problem, this classification problem? So let's see. Okay, here's what it will do. Okay. It's basically what's happening is these y values all get bunched up, and they all map to the same z value. So if I look at z on this axis and the income I, so all these y, the z values corresponding to all of these guys is some value. Okay. The z value corresponding to all of these guys is some other value, and then in between it's linear. Z linearly interpolates in between. So this boundary becomes that. And what's the plus side? This is the plus side. Okay, and this is the minus side. And we see now the linear model perfectly works for this classification problem. And that's what I said earlier, and I've been saying it many times. If you can't solve the problem with the linear model, odds are you haven't thought about the problem yet. Okay? So if you think about saturation phenomena and incorporate them into your features, now all of a sudden the linear model is appropriate. Okay? And that basic idea of transforming your features so that the linear model now becomes appropriate is exactly what the nonlinear feature transform does. Okay? So let's work through the mechanics of the nonlinear feature transform. Okay. And you will see that it's basically the same idea, and it's not a huge rocket science except for the few rules of thumb that we're going to require. Okay. So the starting point is the original data, just like the problem we had before. Okay, so let's call this the mechanics of nonlinear transform. Okay, so you start with your original data, and now think back to the slides. You had this inherently non-separable data set, okay, which is different from the one where the data looks essentially linearly separable, a few outliers, and so you want to tolerate error. When you're dealing with the essentially nonlinear data, it's not that you want to tolerate error in the linear model. You need a completely new model. Okay, so I'm going to illustrate that data. Okay, think of, so I have two features. Let's call them x1 and x2. Okay, and I have, so think of this as 0. So I'll just draw the axis here. Okay, this is 0, and that's 0. Okay, and I will draw my data points. Okay, a bunch of data points. Okay, and we have our x guys, our red guys. Maybe something like that. Okay. So you can think about this as x1, x2, okay, and my feature, my augmented feature x, okay, is 1, x1, x2. Okay, so that's the standard setup. And okay, of course, if we look at this data, we look and say, oh, the linear model is not good. And so one of two things, either you need to tolerate error or you've gotten the wrong features, and we need to transform the features. We need to transform this X guy. Okay. Now, the important message is that you cannot look at the data to decide that. Okay, and we'll discuss this a little bit later. So you have to decide whether or not you're going to use the nonlinear feature transform before you look at the data. Okay? So what you're going to do is you're going to transform this using what we call a nonlinear feature transform. Let's use the Greek symbol phi. Okay, and in this case, just to make things easy to visualize, we're going to transform it to a transformed feature z. We'll call that z. Typically, x is the original feature, z is the transform feature, which I will write as 1, z1, z2. Okay, so I'm going to transform also to 2 dimensions. Okay, so z1 and z2. That's just so that things are easy to visualize. Now, the transformation need not match the dimensions of the original feature transform. In fact, so for example, with the digits data, we took 256 dimensions of original features, if you remember, and we constructed intensity and symmetry, which takes those 256 dimensions down to 2. Okay? So that's an example where the dimensionality of the original feature is much bigger than the dimensionality of the transformed feature. Now, in that case, we did that because we had to. We have a small amount of data, so we need to, lower the dimension so that we can get the link from E into E out. Okay. Here, we're doing it because, in our original 2-dimensional space, we're not going to be able to get E in low. How do we know that? By looking at the data? No. Just, by thinking about the problem, thinking about saturation phenomena, etc., etc. Okay. So we transform to this new feature, and I will write this new feature as z1, z2. And now each of these coordinates of the new feature can be functions of the original feature. Okay. So 2 points. The first point is the dimensions in the new feature can be larger or smaller or equal to the original feature. And each new feature, okay, can be a function of the entire original feature. So we will say that this is equal to, 1. That's the augmented one. Okay. And phi of x, phi 1 of x, phi 2 of x. Okay. So you could have more than, so the transformed feature z1 can involve both x1 and x2. The transformed feature z2 can involve both x1, x2, and if there's a z3, a z4, and so on. Okay. All right. And I'm going to choose for this particular transform, just to illustrate, I'm going to choose the transform, so I'm going to choose z1 equals to x1 squared and z2 equals to x2 squared. So phi 1 of x happens to only depend on x1, it's x1 squared. Phi 2 of x happens to only depend on x2, it's x2 squared. Okay, so let's see what happens to my data. Okay, so in my new feature space, okay, now why I chose that transform is illustrative, okay, because I want to show you what's going to happen to the data. Okay, so in this new space, observe that my new features are x1 squared and x2 squared. So what happens to the sum of x1? What is x1 squared plus x2 squared? x1 squared plus x2 squared, so z1 plus z1 plus z2 is exactly x1 squared plus x2 squared, which is equal to r squared. It's equal to the distance from the data point to the origin in my original space. Okay? And so what it means is that, points that are close to the origin here will have a small value of z1 plus z2, and points which are far away will have a large value of z1 plus z2. Okay, so imagine that I consider I define something. So z1 plus z2 is a line. Z1 plus z2 is basically z1 plus z2 equals some constant. Our lines going in this direction. Okay, and the red points will be above that some threshold, and the blue points are all close, so they'll be below. So these blue points will all map somewhere here. Okay. And these red points will all map, somewhere here. Okay. Look at that. So what did my transform accomplish? It accomplished that my blue points and my red points in my new space, so we will call this the original X space X, and we will call this the transformed Z space Z, and I'm trying to write these as script capitals, but you know, you get the idea. So this is my transformed space. In my transformed space, the blue and red are easy to separate with a line. So I pick a line. So my next step, so this is, you can think of this as the first step, okay, original data. The second step, transformed data. The idea behind transforming the data is that in this new space, the data can be separated by a line, or in general, if it's more than 2 dimensions, a hyperplane. Okay? So in this transformed space, okay, I can separate with a line. So here's my data. Okay, dot. Ah, beautiful. Okay. And now I can find a line that separates. Okay. How do I find this line? Well, I use whatever algorithm I was going to plan on using in the original space, but I just use it in my Z space. So I could use the PLA with Z data points, okay, to find this separating line. Let me call this G tilde of Z. Okay, so now tilde is just to indicate that it's something else. It's not G, the final hypothesis. Okay, and it depends on Z. So it takes in, so this is Z1, this is Z2. So it takes in Z1, Z2, and of course the augmented one. And you know, if you're above this line, it outputs +1. If you're -1, if you're below the line, it outputs +1. Okay, and G tilde of Z is exactly equal to the sign of W tilde transpose Z. Okay, because it's a linear model in my transformed space. So that's very important to understand that. Okay. And in order to get this W tilde, all I have to do is run the linear model in my transformed space. Now, okay, essentially I'm done. I've got my classifier, except, you know, that your client gave you data in the X space. Okay. So as far as the client is concerned, they don't care what you do. So I'm going to put this behind a curtain. Think of this as a black box. Okay. You have done this behind the scenes because, you know, you sensed, you thought that, you know, the data is not going to be linearly separable without looking at the data. And so you invented this feature transform, and miraculously that feature transform succeeded in getting E in 0. That was the whole goal. And you managed to keep the dimensions down to 2. And so you've got your E in versus E out. Okay. But, okay, when your client needs to use your final hypothesis, okay, they don't know anything about this Z space. So the test point comes, okay, so test point comes, x1, let me call it star, x2 star. The test point comes, okay, and it's in the original space. Okay, so how does the client use this classifier that you have built in this weird new space? How does he use that? How does he deploy that in the real world, which is his original space? He's only going to measure, you know, income and age. Okay, but you've done some weird thing to get 2 new features, and you've done some magic here and gotten a separator. But when he needs to use your model, he's going to come with income and age. Okay, no problem. You just need to invert this into this world. Okay, it's not easy to do that inversion, especially if this nonlinear transform is going to have a mismatch of dimensions. No problem. You do exactly the opposite. You tell the client, you know, when you get a new point, here's what you're going to do. You're going to give me the new point. Here's what I'm going to do. I'm going to take this new point, okay, and I'm going to figure out what its position is in my new space. And how do I do that? I can just run phi. Okay, so my new point, let's call it x now. Okay. Let's just call it x generically, even though technically it's the test point on which I'm being deployed. My new point x is going to produce phi of x here. Okay, and now I pump this point into this space. Okay, and I see, are you on this side of the line or on that side of the line? If you're on this side, I'm going to say you're blue. If you're on that side, I'm going to say you're red. Okay. Now, hypothetically, I can play that game with all the points in this space. I don't need to wait for the new point. Okay? So I can hypothetically play that game with all the points in this space. And what you will find is that, all the points that are within some region here, will all get mapped into this point, into this region, and be classified as blue, as +1. So this entire region will ultimately get classified as +1, and anything outside that region, when you implement this nonlinear transform, will be pumped into the red region and be classified as red. And so, this region will be classified as red. Okay? And so, in effect, by doing this process of taking a point from here, looking at where it will land here, and classifying in this space, in effect, I have implemented a boundary between red and blue, which is nonlinear. In this case, something like an ellipse or a circle. Wow. Okay. Look at that. Beautiful. Okay. So this is the effective boundary my client sees. And it's non-linear. And of course, I'm not going to tell them that there's this huge black box machinery behind the scenes here, and actually they're effectively just using a linear model in some, more sophisticated space. I'm not going to tell them that. I'm just going to say, listen, I'm going to give you a feature transform, and when you need to classify, you run your feature transform, okay, and then you run my model in that space. And then when they look at what's happening, when they see the test points, they'll find that all these guys are red and all these guys are blue. And wow, it looks like you did something very sophisticated, not just plain old linear. And so again, I will reiterate. We are just using the linear model behind closed doors. Okay, and the only thing I've added on top of this linear model is this feature transform, showing you the power of the linear model. Okay, showing you the power of the linear model. Now, you will note that in this whole process, the only thing I transform is the features. x1, x2 goes to z1, z2. The color of the points stayed the same. Okay? So let me summarize these mechanics. Okay? The general feature transform. Let me summarize these mechanics. The general feature transform. So, I'll separate out in my summary what's going on in the x space from what's going on in the z space. Okay, so this is the x space, and this is the z space. Okay, and if you were to sort of encapsulate the entire process of pumping up your test point into phi of the test point and then classifying, what are you effectively doing? You're setting z equal to phi of x in this formula, okay? But now you're implementing a classifier in the original space, so we can actually call that our final hypothesis. G of x is equal to g tilde of phi of x, which is just the sign of phi of x transpose of w tilde transpose phi of x. Okay, and that'll appear in this summary. Okay, so in your x space, you have the input, x, which is augmented to 1, x1 up to xd. Okay, so now I'm generalizing. This is the picture for 2 dimensions, 2 dimensions to 2 dimensions, but now let's see what happens in d dimensions. Okay, and in your z space, you get z is equal to phi of x, which is equal to 1, phi 1 of x, phi 2 of x. This is the entire x. Phi 1 need not just depend on x1. It can depend on the entire x. And phi 3 of x, and so on. And you can have any number of dimensions here. Okay, so we'll call the dimensions here phi d tilde of x. So let me just use the convention that if something is in the z space, I will put a tilde on it. So the dimension in the x space is d, the dimension in the z space is d tilde. Okay. Now, let's look at your data. Your data. in your X space, and that's the data your client gave you. Okay? In your X space, it's X1, in the X values are X1, X2, X3, up to Xn, and corresponding to those X values are Y1, Y2, Y3, up to Yn. Now I will emphasize that even though this entire discussion was for classification in which the Y's are plus or minus 1, the Y's can be anything. Okay, they can be plus or minus 1, they can be real numbers, whatever they are. Okay, so the discussion applies to all the three problems we've discussed so far: classification, regression, logistic regression. Okay, and you'll see why. Okay, so now what happens in the Z space? Each of these X inputs, each of these examples Xi gets transformed to the corresponding Zi. So you're going to have Z1, Z2, Z3 up to Zn, where Zi is equal to phi of Xi. What happens to the Y values? Nothing. They stay the same. So the Y values in your data do not change. Okay, so you get Y1, Y2, Y3, up to Yn. So this is your data in your Z space. This is the original data in your X space. Okay. Now, we're going to implement the linear model in the Z space. We're going to implement the model H of Z is equal to sine of W tilde transpose Z. So why W tilde transpose? Tilde, because we're in the Z space. Okay. So you need to fit this model to this data. That's all that's going on. And so you use your favorite model for the linear, for your favorite algorithm for the linear model. If you're doing classification, it's PLA or Pocket or regression for classification, and we'll see other kinds of algorithms for classification. If you're doing regression, it's the pseudo-inverse algorithm. If you're doing logistic regression, you minimize the cross-entropy error using gradient descent. Whatever your favorite algorithm is for the linear model and the type of problem you're doing, you use that model and obtain the weights W tilde, let's call it lin. Okay, so it's the weights for the linear model. Tilde means in my Z space. Okay, and so my final classifier, my final hypothesis in my Z space is G tilde of Z. G tilde, because it's in my Z space, is equal to sine of W lin tilde transpose Z. Okay. Now let's see what's going on in the X space. In the X space, what is the type of, what are my weights? So I get weights W lin equals, okay, let's see, how many weights do I have? I'm going to have weights, I'm going to have W tilde 0, W tilde 1, all the way to W tilde D tilde. Okay, so there are D tilde plus 1 weights. Okay, now, what are my weights in my X space? This is important. There aren't any. There are no weights in the X space. So you're running the linear model under the hood in the Z space and in the Z space only. You're not running it anywhere else. Okay? So then I need to classify in my X space. So I need to have a final hypothesis in my X space. And the final hypothesis in my X space is actually well defined. G of X, okay, is equal to G tilde of phi of X, which is equal to sine of W lin tilde transpose phi of X. This guy is what we were calling Z. Okay, this guy is what we were calling Z. And this final hypothesis corresponds exactly to this process. So if you give me X, I first compute phi of X. That pumps that data point into my new space. I first compute phi of X, and then I apply this classifier. I.e., I decide whether my point that the test point got transformed to is on this side of the line or that side of the line. Hyperplane in general. And that's it. That's how incredibly simple the feature transform is. But once you have the feature transform with the linear model, you can essentially do anything. Okay? And by choosing a suitable feature transform now, we can certainly get E in close to 0. So we are addressing the E in equals 0 issue here with the nonlinear feature transform. That's explicitly what we're using it to address right now. Okay? And then the obvious question is, what about E in versus E out? What about E in versus E out? So let's erase and let's come back and talk about E in versus E out for this nonlinear feature transform.